One. Okay, so we're gonna get started with the online exception four, and we have waited for 7 minutes total, and we're still missing the person called FENG GUO. So we're gonna start with the first presenter, Shavoy.
All right, can you guys see my screen?
Yep.
Yes.
All right, sweet. Hi everyone. This is my project, a recipe generated, a retrieval augmented, and constraint validated recipe generation system. This is the project prototype, track two. And the goal here is to solve a surprisingly difficult problem for LLMs, which is to get them to reliably follow strict ingredient constraints. So again, the problem here is that LLMs are great at, generating recipes, but they often add ingredients that weren't requested, or they just simply forget ones that the user asked for. So whenever use simple prompts like use exactly these ingredients provided, the LLM tends to result or give an output that has missing items or unclear instructions that don't necessarily match what the user asked for. So in my paper, I also addressed the core problem that I'll be tackling here is how we can make LLM-based recipe generation reliable, consistent, and constraint aware. So I'm going to give you a walkthrough of the pipeline and solution that I proposed, as well as a system architecture. So my system works in 7 steps. First, the user enters ingredients. Then that feeds into a retrieval engine that finds similar recipes based on ingredient overlap and fuzzy similarity. Then it's sent into a context builder that feeds instructions from those recipes into the generator. And the generator, so for the prototype, is a template-based system for offline use, but in production and in deployment, it would be the LLM itself. And that would create a draft. And then after that, we would have an ingredient validator that checks whether all the ingredients appear there. Which then feeds into a multi-stage correctional loop that'll automatically regenerate pieces until we get 100% adherence for the user. And then finally, we will output the recipe. And this system here and this process prevents common, drift, LLM drift, where models tend to ignore and kind of drift off of what the user's constraints are. And again, I talked about this in my paper, but the goal here for my project was to not simply just simulate the LLM system, but to show the pipeline logic in a terminal demo as a prototype. So I meant for this to, be a bit of an app, but now I'll show you the basic implementation slash demonstration um, of the prototype. So here, I was again meant to be an app-based system where you could just type ingredients onto, the program or snap a photo of ingredients on a table or in your pantry. So I'll start with the most common ingredients for young adults I searched up, which are this, chicken, eggs, rice, and pasta to get a bit of a healthier meal. And the way this works is that I have essentially two modes here. One is a strict mode where you're asking the program to generate a recipe with only the things listed. And then two is a bit of a flexible mode where you may have time to go shopping to get more stuff, or you are at the grocery store and you just have time to get more things. So I'll start off with the flexible mode. So once I do that, I get 3 recipe options here, and it shows essentially the percentage of what I have. So I have these ingredients, and it would use this percent of ingredients, and then it has additions as well. So let's say I choose one, then it'll again tell me what I have, what I might need, as well as detailed instructions. And then one of the most important things here is this rating. This is one of the rating I guess elements here that'll be used in the retrieval augmented part of the program to help give you recipes built on what you would like. So more customized recipes. So let's say I liked it or it was all right, and then I just go ahead and do that. And then I'll show you another thing. I'll show you the strict mode real quick. Same concept, but it'll just be custom towards only what you have. Yeah. So again, same format, same everything. It's just the recipes are a little bit different. And then again, this is a very basic recipe because I only put in basic things. And that's what I wanted to show that, hey, I only have, very limited options here. Give me something, regardless of, how tasty it might be or how efficient it might be, how nice it is. Give me something that I can make. So, let's say I didn't really like that. So yeah. To wrap it up, the project kind of I wanted to go ahead and show that LLMs can be reliable recipe generators when supervised by a retrieval engine, a validator, and a correction loop. Thank you.
No, thank you for your presentation. I really like it. So I have some question for you.
Hmm.
Um, have you tried running the strict mode without allowing any additional ingredient suggestion so that it use exclusively what the user provides in with the
Yeah.
ingredients?
Yeah. So the reason why I have additional things for like, the strict mode is because that offers a substitute. So, if you don't have anything, but you have something similar to it, the strict mode's like, if you have something similar to, that you didn't know or that you see, you could add that instead. So that's why I have potential additions to it in it. Does that make sense?
Okay. Okay. Yeah. And if, for example, I input a completely incompatible ingredient, for example, chocolate and meat, uh, what happens? You have an error, or the program find a recipe with this ingredient.
Are you saying, sorry, I'm going to clarify, just for clarification, are you asking me how getting the recipe?
Um, oh, so for example, you choose chocolate with fish. So I don't know a recipe with these two ingredients because
Mhm.
I don't think it exists a recipe with these two ingredients.
Oh, yes, yeah. So that's where
Okay,
the LLM would come in
okay,
and try to say, so it's also going to be, so the LLM will be built in here, but this is just the external pipeline to help the LLM be able to follow strictly what the user wants.
okay, okay. Thank you.
Thank you.
If there's no other questions, I can go.
I
Okay,
don't
I'm
think
gonna
so.
go.
Yeah.
Okay. Can you see my screen?
Now we can, Tanvi. It looks like it's still in like the desktop um, mode of PowerPoint.
Yeah, okay. Cool. Um, yeah. So, hi, I'm Tanvi, and today I'm presenting my reproduction of flash attention's core memory efficiency claim. So the big question I'm addressing is, sorry, I don't know why. let me exit out of this and restart the presentation because I don't know why it's just moving to the next slide immediately. Yeah, sorry, I'm just going to restart. So I'm Tanvi, and today I'm presenting my reproduction of flash attention score memory efficiency claim for ECE 570. And the big question I'm addressing is, can we actually reduce transformer attention memory from quadratic to linear complexity? So transformer attention, oh my gosh, has O(n) squared memory complexity, which creates a major bottleneck for processing long sequences. And Flash Attention, published at NeurIPS 2022, claims they can reduce this to O(n) through a technique called tiling. So let me elaborate on that with this slide. Standard attention creates an n by n matrix. That's where every single token attends to every other token. And this quadratic growth is the main bottleneck preventing transformers from processing longer sequences. So to put this in perspective, for a typical GPT-2 model with 1,024 tokens, that's over 1 million values in the attention matrix alone. Scale that to 8K tokens, and you're looking at like 64 million values. And this is why standard transformers hit memory limits so quickly. So Flash Attention claimed that they can reduce this to linear memory through an algorithmic technique called tiling, and that algorithmic technique was what I tried to validate. So I implemented chunked attention in pure PyTorch to sort of isolate the algorithmic insight from the hardware optimizations. The key idea is really simple. Instead of processing all the query tokens at once, I process them in smaller chunks. And the algorithm, as you can see, for each chunk of the query matrix, I compute attention scores with the full key matrix. Notice that each chunk only creates a small attention matrix, chunk size by n, and instead of the full n by n matrix. And after applying softmax and multiplying by the values, I write that chunk's output and move on to the next chunk. The key insight is that I'm processing Q in chunks, but I'm attending over the full K and V matrices. This maintains mathematical correctness while reducing peak memory from O(n) squared to O(n), or O chunk size times n. And I evaluated this on two benchmarks, so synthetic random tensors that I created to test the pure algorithm in isolation. And then I also tested it on real IMDb text sequences to validate that it works on actual language data. So here's my results. Let me walk you through this visualization. On the left panel, you can see memory usage for both standard and chunked attention across different sequence lengths. So notice how the red line for standard attention curves exponentially upwards. That's the quadratic growth. The green line for chunked attention stays nearly flat. That's the linear scaling. That's exactly the O(n) squared versus O(n) behavior that we predicted. The middle panel shows memory reduction percentages as sequence length increases. The reduction does get better with longer sequences because the quadratic term dominates more as n grows. On synthetic data, I achieved around 55.7% reduction, on average 78 on certain runs, which was the excellent tier on my project primer, so I was satisfied with that. And on real IMDb text sequences, I got even more, around 84.1% on average, 87.6 for this run, at the same length. So this validates that the approach does work on actual language data with real structures and not just random tensors. Also, across all 13 test configurations of synthetic and real data, I maintained perfect correctness with a cosine similarity of 1. This proves that chunked attention is exact and not just an approximation. So what does this mean? First, I successfully validated Flash Attention Score claim, which is that tiling really does reduce memory from quadratic to linear complexity. The 84.1% reduction proves that algorithmic insight works independent of hardware-specific optimizations like CUDA kernels. Of course, there are limitations. The paper requires CUDA kernel optimization, which was beyond the scope of this reproduction, so I don't achieve the speedup gains. And I'm also testing on a single GPU and focusing on the forward pass. But the memory reduction, which is what I set out to validate, is definitively confirmed. So, just as a conclusion, I successfully reproduced flash attention's memory efficiency claim. Chunked attention achieves 84% memory reduction on real text sequences while maintaining perfect mathematical equivalence. So this validates that the core benefit comes from algorithmic restructuring, which is what the paper claimed. So thank you. Any questions?
Nice work. I did have one quick question.
Yeah.
And it was how exactly does chunked attention compare to like other memory efficient mechanisms like flash attention or sparse attention?
Uh, I guess in the real world pretty well because I believe now flash attention is used directly in training a lot of the newer models like GPT-4, the more recent Tiny Llama models. Um, how does it work compared to so do you mean how does chunked attention work compared to flash attention?
Yeah, just like,
Um,
for like why'd you choose chunked here?
oh, so that was a part of the paper itself.
Hmm.
I guess flash attention uses chunked attention
Uh-huh.
in its implementation. It's just that flash attention, the paper itself, takes this a little further with how it optimizes with the GPU and then recomputes certain um, values during the backward pass.
Uh-huh.
So
Okay.
that instead of storing intermediate gradients, they recompute them to the backward pass. So I guess that's the difference between just regular chunked attention and flash attention.
Gotcha.
Does that
Thank
answer
you.
your question?
Yeah.
Okay. Okay. I guess if there's no other ones, then we can go ahead.
Can you guys see the full presentation screen?
Yeah, we
Yeah.
can.
Yeah.
Okay, so is my audio good? I just forgot.
Great.
Okay, fantastic. Okay, so I'm presenting a project on lift estimation using a physics-informed neural network on a burst scale flapping wing vehicle. So the motivation behind this is that we see UAVs and planes, they have really well-known dynamics, such as having a propeller and a high aspect ratio wing. And so the question that's naturally asked is, what kind of dynamic model will we choose if there is very little known information about this platform? So, are there any existing literatures that could inform us about the complex aerodynamics of a flapping wing vehicle? And question two we can ask is that could we leverage any machine learning techniques to accurately predict lift during flight, given some known features? And that lead us to a physics-informed neural network, or short for PINN. So this is the platform that we're using in this study. It's a 2 degrees of freedom flapping wing vehicle that we designed in the lab. And the next video, we'll see how it's able to actuate its wings, and we will be recording some data on a six-axis force transducer, and we'll be able to have raw lift data from this experiment. So yeah, as you can see, the flapping vehicle is able to have an upstroke of 20 degrees, downstroke of 30 degrees, and on top of it, it's mounted on a six-axis force transducer. We're able to obtain raw lift values from this transducer. So here is the raw force measurements and flapping cycle plotted on top of the flapping angle theta, and you can clearly see the upstroke and downstrokes trend 30 degrees and negative 20 degrees, and that we have stroke reversal happening at this point where we see instant changes in the flapping angle, and that results in a net zero lift because it is at the transition period. So that is good with our intuition. And all the data has been filtered through a Butterworth filter at a cutoff frequency of 30 hertz. So first, we can talk about the physics-informed part of this study. So we'll be using a very traditional Blais-Alman method for lift estimation. So essentially, we'll be cutting the wing into n pieces or n blades across the span of the wing profile. And at each span-wise location R, we will have the information for the chord length since the wing we designed the wing profile, the leading edge and the trailing edge. So given C of R at the span-wise location R and the leading edge shown in blue and trailing edge shown in orange, we can write down the sectional lift at each blade element at each panel. And given the lift coefficient, D of L here, we can then use a Riemann sum to sum up the total lift across one flapping at one angle, theta. So here we can get the total lift generated through one flapping cycle using this Blais-Alman method. And plotting on top of the filtered lift obtained from the force transducer, we see that the estimated lift at times underestimates and at times overestimates the actual lift that we obtained. But it is especially bad at times where where there is net zero lift during the actual flapping cycle, but we are estimating a value that is much lower. And here as well, when there is positive lift, we tend to overestimate the lift value. But the estimation isn't too awful because it is bounded. And we see that it is on average having more positive lift force than negative, meaning it should be able to lift the vehicle up to stay in the air. So that is a good start for a physics-informed neural network. So next we'll be implementing this framework where we'll have two hidden layers, and we'll be using most importantly, we'll be using a bidirectional RNN, and it incorporates a forward and backward pass. Instead, like since RNN is very useful if you have a time series of data, and given this that we have the entire time series of data for this experiment, we are able to do a forward and backward pass, which makes the prediction much more accurate. And the second noteworthy part of this network is the use of leaky ReLU instead of a traditional ReLU. So a traditional ReLU I have implemented tends to estimate lift to be very much have a mean of zero because that is the safest estimation, but that is due to a dineuron problem. So as we have seen during one of our assignments, using a leaky ReLU is able to solve the issue. And finally, we have the cost function or the loss function shown in the red box. So it composes of three different loss functions. One is just MSE loss between prediction and actual. So between lift during the physics and the actual measurement, it will be a simple MSE loss. And second, we'll be adding a Lagrange multiplier lambda 1 to the slope, meaning I want the model to be able to predict the sudden jump and spike of lift or a sudden loss in lift during upstroke and downstroke cycles. So we'll be taking n equals to maybe 10. I think I used 10 in the actual model to do this averaged slow prediction, and we'll be doing a MSE loss on that. And finally, we'll be using a lambda 2 for the Lagrange multiplier for the physics part, meaning how much do we trust the physics in this sense. So here is the loss function, training loss function. As we can see, it drastically decreases. But the most important part is to the right, where we see in the past where the physics estimate is underestimating massively when the lift is actually zero. The physics plus the residual correction in this PIN and physics informed neural network is able to better estimate the when the lift is low. And however, it's also obvious to see that it has an offset to where it's predicting the lift is positive. So it has a very constant offset that I can attempt to fix in the future work, and it has a lower magnitude. So there are still issues in terms of tuning and maybe better cost function, but overall the result is shown to be much more promising than just a physics-based approach. Okay, so that's my presentation. Are there any questions?
Yeah, hi, I had one. Great presentation, by the way. You mentioned you had raw force measurements.
Yes.
I was curious, how noisy were those measurements, and did you do any pre-processing or filtering before training? I think you said the PINN, or does the physics constraint smooth out noise
Yep, that's a great
internally?
question. As a background, this measurement device here in silver, this circular one, it's able to capture at 10,000 hertz, and we applied a moving average filter of 100, so it will average every 100 sample. So the data that's coming out of the filter is essentially 100 hertz. And on top of that, in the post-processing, we applied um, um, a Butterworth filter of cutoff frequency of 30 hertz to smooth out the data even more. So the data that you see here in blue, where the lift force is, are actually after 2 rounds of smoothing. One is the moving average filter from the sensor itself, of averaging 100 data points. And the second is a Butterworth filter. So yeah, this is we're using a averaged and smoothed out data to train this model.
I see. Thank you.
All right. Um,
Awesome. Thanks, Jeffrey. Hey, I'm going to try to, I think I'm next, so I think I'm going to try to share my screen. Okay, can you confirm that you can see it?
yes.
I know it's on like the desktop, PowerPoint view right now, but just confirming.
Yeah, if you want to full screen it, we're not seeing the full screen yet. There we go.
Is that good?
Yeah.
Shoot, now did it go back? Okay. It's still on the non-full screen, right?
No, it's not
Yeah.
full screen yet.
Okay. Guys, can you give me just 1 second? Sorry. Okay, I think I'm good, and I'm on full screen, correct?
Yes.
Okay, sorry about the delay. All right, so let's kick in. So I did a tiny reproduction study, again for ECE 570, and the title of it is The Achilles Heel of Multi-Head Attention, specifically the scale dependency of attention mechanisms. Um, so um, I based my tiny reproduction right on the very famous attention 2017 paper. Attention is all you need, and that attention is all you need paper really focused on multi-head attentions, superiority to single head attention. So, and the reason really for that original claim, right, was because of how diverse of a subspace, right, multi-head attention can capture. Specifically, the paper used 8 heads, vice the 1 head of single head attention. My question was, hey, is this superiority universal? Really specifically, does that still hold in a resource constrained or a tiny environment like our course project required us to have? So my hypothesis was that hey, that complexity in the case of multi-head attention may actually be a liability in resource constrained environments. Um, so then to kind of take it away, what I did, so I utilized the Opus Books German to English data set. So it is a real world data set, but it's a smaller scale translation task, which I thought would be good at highlighting if there's a complexity issue with multi-head attention, vice single-headed attention, and if there's like a generalization issue there. And again, it was kind of true to the direction that we got to make it a tiny reproduction of whatever research paper, right, we were looking at. So the parameter count was about 120 million. I used a A100 L4 GPU on Google Colab Pro really to run the code. I did it in 6 acts really. So first of all, obviously the multi-head attention splits its capacity over those 8 heads. But really, the 6 acts that I went through was so I started off with a 3-layer model, kind of just standard dropout sequence length of 128. I saw overfitting there in multi-head. So basically, single head performed better than multi-head. So I kept trying to tease out, hey, why was that? I then increased that depth to 4 layers. Basically, saw the same thing. I then went to I tried to increase the regularization. So I increased my dropout. I switched to like a greater weight decay. I still saw now actually both models underfit that time. So perhaps the regularization there was too strong. I then moved on to basically like what I thought was a Goldilocks regularization. So I brought the dropout back down to 0.1, but I did keep the weight decay. This was actually the most stable. It's where really multi-head performed the best, but multi-head still lost. And so basically that kind of confirmed that the structural deficit was real. I then went on to increase complexity because I thought, hey, maybe increasing complexity up to a sequence length of 256. Really, the reason for that was to test if multi-head was failing because the task was too simple. And I thought, hey, by increasing the sequence length, it's going to at least require tracking more complex dependencies. Once again, multi-head overfit. And then the final thing that I do is so the attention is all you need paper. They actually used a warm-up, like a decay learning rate scheduler for the multi-head. So I attempted to implement that as well. And in fact, single head still won conclusively, as I'll show on my next slide. So basically, now I'm pulling here Act 4 which for me was like that Goldilocks regularization that I discussed, and it was actually where multi-head performed the best relative to single head. So you can see, right, that solid red line. You see how quickly um, of basically a loss reduction that multi-head gets. So that's multi-head. But unfortunately, as you look at that validation loss, right, which is the dashed red line above, it didn't come really close uh, to as good. And frankly, obviously, that's because it basically stalls out and barely improves. Really, frankly, the multi-head throughout, it was so incredibly good at memorizing the training data, which was not that large, right, of a volume that again, it basically memorized it instead of actually learning it. So it struggled immensely in validation as it compares to the single head attention, which you can see the loss for that is the solid blue line, and then the validation, right, is the dashed blue line. So again, the quantitative analysis really just it confirms the story that even in really the most rigorous experiment, which was that Act 5, where we increased the sequence length to 256 tokens. That's something that multi-head should dominate. Single head still won. Um, um, and so basically, in summary, unfortunately, complexity can be a liability, especially in tiny regimes. Basically, these extra heads ended up just memorizing the noise rather than actually like learning it and generalizing it. Whereas single head, basically pushing everything through a single head acted almost as an implicit regularizer there, which allowed it to actually learn better rather than just memorize. And so, really, I think the takeaway here is that even though multi-head attention clearly is so much better for most of the large scale models that probably we're going to do research on, if you have a smaller scale model, you should at least be determined whether it's actually better or not by testing that. So that's what I had to present. I'll open it up for any questions.
Great presentation. I do have a question. So for this multi-head application, where do you see, for example, in day-to-day research and maybe in the area of robotics, which is my main interest, where do you see an application of this kind of model?
Yeah, it's a good question, boy. And maybe you could help me out. I think with robotics, boy, it seems like there are so many parameters there that potentially robotics may be a space where this is um, much less useful because of the number of parameters that I would just estimate that you would have in a robotics setting where there's so many degrees of freedom, et cetera. I would think that it would actually be more powerful on, again, a simpler model, something like a structural engineering, right, type framework where maybe you're analyzing the behavior of a building or something like that, a much more rigid structure that's going to have fewer parameters. Again, I don't have a deep background in robotics, so uh, so
No, I mean
maybe I'm
that's
off base
perfect.
on what I'm answering there, but that's kind of my intuition.
Yeah, that's a good answer. Thank you.
Yeah, great. Any other questions? Okay, great. Thanks very much for listening. I'll turn it over. I think Tanguy, you're next. Hopefully, I pronounced that correctly.
Yes, I'm next. So I will share my screen. Okay, can you see it?
We can see the screen, Tanguy. Looks.
Okay.
Um, yes, we can.
Okay. Okay. So, hello, my name is Tanguy Ormand. Welcome to this presentation on the reproduction of the paper Neural Physics using AI libraries to develop physics-based solvers for incompressible computational fluid dynamics. And the core challenge for this project was to verify that we can repurpose modern AI libraries to solve classical physics equations faster than traditional CPU solvers. So my goal was to reproduce the key graphical results of the article for the 2D advection diffusion equation that we can see on the top, which governs how quantities like heat or smoke move in a fluid. To solve this numerically, I use the Crank-Nicholson scheme, and this is an implicit method, meaning it is unconditionally stable and allows for large time steps. However, implicit methods require solving a large linear systems at every single time step. So the innovation of the original paper and my reproduction is how we construct the operator L. Instead of standard loops, we derive the finite difference stencil and implement them as a static 3 by 3 convolution kernels. So why don't we need these complex solvers? If you use a simple iterative method like Jacobi or Gauss-Seidel, it smooths out high frequency errors very quickly. However, as we can see at iteration 20, it stagnates on low frequency errors, which represent the global trends. Um, this is where the multigrid method comes in by transferring the residual to a cursor grid. And those the low frequency errors become high frequency error, which are easy to smooth out. And this allows us to solve the system much faster. So I implemented this multi-grid V-cycle using a structure that mirrors a unit architecture. On the left of the U, we can see the encoder path that perform a restriction using average pooling, and that move error to a cursor grid. On the right, we can see the decoder path performing a prolongation using interpolations to come back to the initial grid. And we have also the big gray arrows that allow to concatenate the informations to have better information at the end. And we have finally we have the blue arrows that dumps out high frequency errors by using a CNN convolution. So I validated my model with two metrics. The first one is a numerical accuracy by simulating a pure diffusion case over 100 seconds. And as we can see on the chart, I compared the peak value of my CNN-based solvers against a traditional reference. And the results in the table show an absolute error consistently around 310-4, confirming that repurposing CNN kernels maintains a good level agreement with analytical baseline. And my second matrix is the time performance. So I evaluated my model on Um, and I evaluated this model during 50 seconds of physical times, and the CPU take 9.29 seconds, and the GPU take 0.58, which results in a speed up of 16. So I successfully implemented a model which is as accurate as the CNN, as the classical CPU solvers, and which is 16 times faster than a traditional CPU solver. So thank you for listening to me.
Hey, Tangi, one really impressive presentation. I think it's super cool how you connected, basically like, AI layers to physics steps. That I think it's really neat. One question I had for you, the experiment setup that you chose, basically was this working on a pretty like nice square grid. Um, from a fluid dynamics perspective, do you expect that it would be harder to adapt this approach for like more complicated shapes, like airflow around a car or an airplane wing, for example?
Yes, because the grid will be much more complicated. So if we have a, if we study a plane, for example, with a complicated geometry, in CFD we use finite element method, or which can be adapted more easily to complex geometry. And the multi-grid method is used for simple geometry with with no with no particular shape in the in the in the area we study.
Okay, yeah, that makes a lot of sense. Thanks for answering that question. I didn't have any other questions. Thank you.
Okay, thank you. So I don't know if the last person will come to the presentation.
Yeah, I think that's it. I think he's just maybe he has a personal situation. Maybe he already explained to Professor.
Okay.
Um, I'm gonna end the recording now since everyone is done presenting.